Okay, this is our third uh, video for chapter 6, and we're looking at standard state. So, uh, doing calculations all the time, it's really difficult, but I remember I said that we have state functions. So you can do enthalpy, you can look at entropy, various things, and well, we've only talked about delta E and delta H. So H and E, we can do them in the laboratory, and we can pick a state, a standard state, and then we can relate them to the standard state. It makes the math much easier. And it also prevents you from having to do the work yourself, so it's kind of nice. So standard state for a gas, it's the pure gas at a pressure of exactly 1 atmosphere. So this has been an issue actually for international collaboration. So here in the United States, our standard state is 1 atmosphere, which is 101.3 kilopascals. In Russia, they've done standard states too, but their pressure is 100 kilopascals. So they're close, but there's a slight difference. So depends on where you're at. If you move to Russia and if you're working for doing thermodynamics for a Russian company, their standard states might be slightly different than ours. Liquid or solid is a pure substance at the most stable form, a pressure of 1 atmosphere, at temperature at instance of interest, usually 25 degrees Celsius. So for instance, carbon. Carbon can be graphite, it can be diamond, it can be nanotubes, it can be fullerene, CH6c or C70. The most stable form is graphite. So the standard state for carbon is graphite. Oxygen can be ozone, it can be oxygen radical, it can be O2. O2 is what we use for the standard state. For a solution, it's the solution at 1 molar. So the standard enthalpy change, this is when everything was in their standard states. And the enthalpy of formation, this is how much it takes to make something. We calculated that for propane last section, last whatever, 6b. We did that for propane. And another definition, so pure element in the standard state, the heat of formation is 0. So which lets you know enthalpy. Enthalpy is a relative scale. So remember, like degrees Celsius, that's a relative scale. 0 degrees Celsius is the freezing point of water at 1 atmosphere. And so enthalpy, we pick zeros for that. So other things, so entropy, which we haven't studied yet, that's an absolute variable, or absolute function. But enthalpy is relative. So here are some standard enthalpies of formation for that. You don't have to memorize any of these except for elements. And for any reaction, the sum of the moles of the products, enthalpy of formation of the products, minus the sum of the moles of the reactants, enthalpy of formation of the reactants, equals the standard heat of reaction. So something to note, this capital sigma, this means sum. So like we have sigma n equals 1 to 5 of inverse n, and that equals going across there, you just add them together. That's like a math formula. There's capital pi, that's a geometric series. It's the same thing but multiplication. So let's apply this formula for this equation. What is the delta H reaction for this ammonia forming ammonia oxide, nitrogen monoxide? And this is also an important reaction. So ammonia, well, let me tell you some of the history of this stuff. So around the year 1900, we were facing what's known as a Malthusian catastrophe. That's when the population outgrows its ability to provide for itself. So in this case, we were running out of the ability to grow enough food for the population. The population of the Earth was around 2 billion people. And organic farming just didn't cut it, so we were supplementing the organic farming with nitrate fertilizer from South America, but obviously that's not sustainable. So the leaders of the world were worried. Let's put science into it, and science was searching for a way to get more nitrogen fertilizers. So that was the thing. This is what we're limiting. We need more nitrogen fertilizers. And then in the BASF in Germany figured out that if you can use an iron catalyst to make ammonia. And that was a big sigh of relief because now we have all the nitrogen fertilizer we want that we can make from air and natural gas. So then what happened though after that is after ammonia was formed, it could react with oxygen to form nitrogen monoxide, and we can react further to form more nitrates, or nitric acid, I should say. You can add this and burn it some more and make NO2, and then add water and make HNO3. And nitric acid, well, like for instance, if you mix nitric acid with glycerin, you can get that in any fat, you get nitroglycerin. You can take toluene and mix it with nitric acid and get trinitrotoluene, also known as TNT. So suddenly Germany had the ability to not only feed themselves, but also had the capacity to make lots and lots of explosives. So what happened? I mean, yeah, I know there's Archduke Ferdinand, about the assassination of him, but without the chemistry know-how, Germany could never have fought World War I. It would have been over in a couple of months, but it dragged on for years. Because that was the British's plan. Like, oh, Germany wants to fight. Well, we'll just blockade them. We've got an amazing navy. We're just going to blockade them. No nitrates from South America, and they won't be able to feed themselves, and they won't be able to make bombs, and we'll all be good. But the chemistry know-how of Germany allowed them to fight longer. So that is one of the unfortunate things of science, I guess. But okay, let's talk about this reaction. So what is the delta H for this reaction? So it's the delta H0 reaction, RxN is reaction. It's going to be 4 times the heat of formation of NO plus 6 times the heat of formation of water. So, and minus 4 times the heat of formation of ammonia plus 5 times the heat of formation of oxygen. Okay, I guess I didn't. I keep on putting parentheses there. I'll put those here. So the heat of formation of an element is 0, so oxygen is 0. And some of you know I'm just applying this equation to that circumstance. That's all I'm writing. I'm writing it out. And now we got to get the numbers. Let me see if I can read this for the numbers. So NO is, so this is 4 times NO 91.3 plus 6 times water, is it under, and water, okay, and times 241.8, and minus then, so NO is positive, yeah, minus then ammonia's 4 times, what is ammonia, minus 45.9. Okay, let me go back. And, oh, one thing to note, you have water vapor. If you look at water, there's 2 forms. Make sure you pick the water vapor and not the liquid water, because they are different. And then you just throw these in your handy-dandy calculator. And did I already write this? No. 4 times 91.3 plus 6 times minus 241.8 plus 4 times 45.9. And that's minus 902. Equals minus 902 kilojoules per mole. And that's the answer. So, I guess I'll go ahead and put my calculator on there for you. Okay, so I put the calculator on there for you. So let's see if we can do this reaction. So this is also known as the thermite reaction. So you can use this to generate liquid iron. And see if you can do the delta, the heat of this reaction. So, and you notice aluminum and iron, although I simplified it, the iron is usually liquid after this reaction, but make it simplified. It's going to be the sum of the moles of products, enthalpies of products, minus the sum of the moles of reactants, enthalpy of reactants. So our delta H is then going to be the heat of formation of sapphire minus the delta heat of formation of rust. And that's going to be equal to this one. And it's very, very exothermic. So if you want to have some fun, look up the thermite reaction on YouTube, and don't do it at home unless you are very, very careful. So, short video. I will see you then for chapter 7. Aloha for now.